Yeah, my name is Pim Verkerk. I work at the Pronto project in the Port of Rotterdam. Our project focuses mostly on optimizing the traffic of ships in the Port of Rotterdam, but also globally, and tries to reduce waste and emissions that way. Of course, we are hiring as the Port of Rotterdam and probably Codestar too. So if you don't know where to spend your time, it's probably possible to join us. And yeah, without further ado, I'd like to introduce Joost, who's going to tell something about Kotlin and coroutines.
Yeah,
right?
coroutines. Yeah.
Cool.
Coroutines. Yeah, so coroutines during the having drinks, I spoke to some people. So I know some people in the room who come from a mindset of Haskell. Some people come from Java. I'm sure some from JavaScript. So I'll try to build bridges to the stuff you know. I guess we have some time, so if I'm unclear about something, shout out, and I'll try to work with it. So coroutines, a little bit of context. Coroutines, it sounds a bit abstract, but you can compare it to lightweight threads for now. And of course, I'll elaborate much more. And another one to give a little bit of context. What are the things we are thinking about? So this we have a computer in the middle, a server. On the left is a client who makes a request. We all know the drill, right? And then in the back end is either an API or a database or whatever. And so while there's an HTTP request coming in, and in the middle, during the whole processing of the HTTP request, the thread of execution is taken up. It's occupied, and when you think about it, most of the time it's waiting for the back end. And that's a waste. So tonight is about what are the alternatives, especially in the Kotlin world with coroutines. But I'll, make some. I've got experience in different ways of concurrent and asynchronous programming as well. So I'll try to, compare a little bit how those work. So. This is something better in that sense, because in the middle, as you can tell, the thread of execution is free to do something else. So that's a little bit of the context what we're talking about. So let's dive in with some code, right? We start out. If you don't know Kotlin, fun is a function. This is our main, like in Java, static main, and we start out first in when I run my static main Java program, from the command line. I not always think about it, but it's being run in a single thread. So that's how we start out here. We're in the world of JVM threads, which are operating system threads. Why that is important will become clearer later on. So this is where we, in the Kotlin world, where we transition to the world of coroutines. So coroutines are lightweight threads, you could say, and where in the world above here, we should be careful about not blocking that precious heavyweight thread, like you saw in the diagram. Here we're in a world where we can, we have plenty of threads, and weigh hardly anything, so we can suspend at will. Little bit of a note, we start a coroutine scope here. Kotlin has this feature where a block, so the accolade, where the accolade starts, that's a block, right? But in Kotlin, that can be an anonymous function that's called on an object. So that's a little bit of a twist, also when you come from Scala and stuff like that. And it's really powerful, actually. But that will become clearer later on as well. So this is where we start a coroutine. And this is so launch is the coroutine builder where you start a fire and forget coroutine or thread. So that means that we don't care about the outcome, we just kick it off and continue. So in execution, we started off here and immediately afterwards, I think I need to point. We kick it off here and execution continues immediately here before this has happened. So it's a bit of a split off of your execution focus, if you will. Then here we create a new scope. So we were already in the root scope next to run blocking. And here we create a child scope. So within, when you're programming coroutines, you're always in this hierarchy of scopes. And why will become clearer later on. And then within this scope, all the threads that we start there will be completed or ended or cancelled at the end. So that gives us, it's basically like the scoping of memory as well on a stack, right? So you know for certain that here, whatever you started has ended. Why that is important, I'll elaborate more later on as well. So within our coroutine, we can call suspendable functions. And the idea of suspendable functions is, the name says a lot, I guess. They have potential pauses in their execution. And that means that while they are suspending, as the word says, they can be rescheduled to a different thread or put temporarily on hold because, for instance, we're waiting for that backend that takes some time. So those are the points where execution can change. Does that make sense? I'll elaborate more later on as well. So focusing a little bit on, we were calling this function, right? And reading Kotlin function types, the suspend keyword is super important. So it's a bit like in the Scala world that a function returns a future, or in the Java world a completable future, or a promise in JavaScript. So this is the equivalent. It's an asynchronous suspending function. And as it goes with asynchronous programming, it's super cool, but if you call a suspending function, you have to be a suspending function as well, etc., etc. As we can tell, it returns a job, and a job is basically something that allows us to cancel it, for instance.
Perhaps I don't fully understand it. What's the point of creating a non-blocking delay method?
I'm not creating it. It's part of the standard libraries. So I wanted to show you that when you call a suspending function, that's the point, you know, that what they are suspendable functions, and that's a point where the coroutine, the thread, can suspend, you know, stop executing for a moment, and then later on resume. So it's like thread sleep.
Yeah.
What do you use it for? For demos.
Or tests.
Yeah, or tests. Yeah, exactly. Asynchronous tests. Yeah.
Okay.
Does that answer your question?
Yeah.
So, this is what I already said. So the suspend keyword is really part of the type of the function. So when you do functional programming, you often ignore the name of of a function. You look at its shape, and so the suspend keyword is part of the type. In Scala, like with implicit functions, implicit will be part of the function type as well. And so to me this is really interesting. The suspendable function, I can call it from another suspendable function, and there's no wrapper around my value. So you know, in Java, have people developed with completable futures before, for instance, or you know, an reactor mono. Front-end promise, and so that's really powerful. I think I'll show more about that later on.
What about the third?
The third?
That's basically the equivalent of feature, or what do you say in Kotlin?
So I'm not sure what. Maybe my sentence was wrong.
Yeah, because you said job is basically almost the same thing as feature or completable feature, but you have also a thing like deferred.
Yeah, exactly. Yeah. I'll show you deferred later on.
Okay.
Yeah. So currently, I started out with coroutines that are fire and forget. So you just kick it off, and the end result is you don't see directly. And there's also a way of with deferred you can do parallel, concurrent processing and combine the asynchronous results. But that I'll show that. So, let's come back to that issue, because it's different from the a future or a completable future. So we'll see. So this is the fire and forget. Little bit about Kotlin. It starts. So this is an extension function. And that means that it's called, we call launch on an implicit this. So some people malign Scala for using implicits, and I like to joke that Kotlin embraced the one implicit argument that object-oriented developers are familiar with, this. And so in the code that we looked at, here, this launch function is called on the coroutine scope. And that's a really powerful mechanism that's used a lot in Kotlin. So it's launched within the scope. And it's handed a context, and that's used for a few things. So for instance, that job reference that we saw can be propagated through this. But for instance, also the thread pool, basically, that it's running on, will run on, which is called the dispatcher in Kotlin coroutines. But for instance, if and when transactions will be supported. That's a candidate for this kind of contextual data as well, right? You know, in the Java world, for instance, you have thread local, so it's a bit similar to that. And then this is where the magic happens. So if you recall, the launch function was handed a block, right, between accolades. And so when we look at the type of that block, we see the keyword suspend, which is part of the function type here. And we see that it's called on the coroutine scope again. So which means that what happens within there will be part of that hierarchy of scopes again, which is important for the control of all the asynchronous processing that's going on in the block. Does that make sense? Okay, run some code. Wish me luck. Okay. So this is our code again. Let me embiggen it a bit. Okay. That's not what I was looking for. I'm in the wrong one, sorry. Okay, is this readable? So it's the same code. Yeah, let's just, oh yeah. I'll elaborate later on, but you can already see that the IDE gives us extra clues about the asynchronous behavior of this code. But I'll elaborate later on. Okay. So let's run it. So this is my poor man's RX marbles. We see that it starts out in a main. The red code is the main thread, and then it's basically a hierarchy that it executes. So let me. Here we are. So that's a really simple example of asynchronous processing with coroutines and suspending functions. So let's do something a bit more realistic and useful. So one of the things is normal sequential processing, but combining multiple functions, which is what we're constantly doing, right, as developers, but also concurrent processing. Notice that I'm not saying parallel processing, because people who know, who are really into computer science say, well, you could run it on one core and then it would be concurrent, but not parallel. Well, yeah. We can discuss that more over beer, perhaps, but so it's interesting, right? When you're doing a lot of calls to other systems, and some of them are quite slow. It can be quite handy to have it quite easy to run them at the same time, and have a shorter processing time. Okay, so yeah, this is a really simple example. We have first we get the products, the names of products that I don't know, customer or citizen or whatever has, and it's a suspendable function. And for the demo, it's 100 milliseconds. And then we have the follow-up function. You see where it's going, right? We'll have to get for every name a product. So how do we combine these? So when you do Scala, you'll have futures that you need to combine using for comprehension. And so let's see how it works here. Yeah, I'm sorry, it's not more than this. So if you're in a suspendable function, you can just call the suspendable function that you care about, and you just get the value that you were looking for. Yeah, so that's to me that was quite impressive. Yeah.
So excuse me. The top one is a suspended list of strings.
Yeah, so good question. When you think about it, what goes on under the hood? So on a code level, well, you know, I typed the type. It's a list of string.
Yeah. So if I'm from JavaScript, I would say await for a list of strings.
Yeah, so a little bit of a segue.
Okay.
No, that's fine. Do you guys know what async await is? It's used a lot in C#, for instance. It's available in ECMAScript.
6, I believe.
Yeah, really powerful. So when you're dealing with promises. And basically, coroutines are as if generator functions and async await had a child and it had all the powers of both. So it's it's you know, it's a generalization of those. Yeah, yeah.
But the bottom one is also interesting because it's not you suspend for a list of strings, but you get a list of suspended things. Or am I mistaken?
Yes and no. So the powerful thing is it is a list of string initially, and I can just map them and I have a list of product. So the reason we're talking about this, if you're working with completable future or promises, etc., this is a little bit of a thingy. You need to jump through some hoops, right?
You get the future of list of future of product, and you have to somehow.
Yeah, exactly. Yeah, stuff like that.
Yeah.
And so in that sense, it's really a list of product that you have here. But so I'm getting a little bit ahead of my talk, but you know, that's fine.
Back to it.
Yeah, we will. But under the hood, all of this code is suspendable and asynchronous, and I'll dive into how that works. But it's powerful, right? It has to be in a suspendable function. That's important to notice. Okay, so a little bit more complicated. So you spoke of deferred, right? So one of the prime uses is, so here we have the product names, which takes, I don't know, 100 milliseconds. And for every product, it takes 500 milliseconds. So we want to do those, start them all, and then start collecting the results instead of first calling one, getting the result, then the next. So how do we do that? We map them, but the asynchronous call we wrap in async, and async returns a value. So where launch is fire and forget, you know, here we get the value of the block of code, And then the strange thing is, at least, I came from a perspective of Scala development, we just await. And so in the Scala world, await result, that's a no-no, because then you're blocking the thread. And you only have a few threads, one per core. So pretty soon you brought the whole application to a standstill. So here that's not the case, because that await is basically just suspending until a result will occur. So it suspends the coroutine, but that's okay because you have hundreds of thousands of coroutines potentially. And the memory they eat up isn't that much either. So we just await all of them and return the result. So one tricky thing, it has to be in a coroutine scope. Remember this hierarchy, and that's because here we're launching coroutines again, and they do need to be in this hierarchy. Otherwise, we'll have a memory leak. Mm-hmm.
So it's basically something like nested scopes, and the child scope have access to the parent scope indirectly.
So the root scope has children, and those are all the other, the lower scopes. Yeah, they add themselves to the implicit this. Yeah, so that's a pattern you often see in Kotlin, the builder pattern, and yeah. But so we don't have a reference here because we're in a suspendable function, but we don't have that receiver. Remember, before the name of products, there's no coroutine scope dot. So that's why we start a new scope here, but that's a child underneath the outer scope. Yeah, and just await.
Just a question.
Yeah.
Why don't you do that?
Why don't you do what?
Extend the coroutine scope?
Good question. I thought that was handy as well, but then suspendable functions have a coroutine context, and when you extend coroutine scope, you also have a coroutine context, and that's ambiguous. So the compiler will say no. Yeah. And so these are all suspendable functions. So these are the suspension points of this function. So that's where the scheduling is able to stop this coroutine, this coroutine, and start doing something else. So this is cooperative multitasking and not preemptive, if that's familiar.
Question, Joost.
Yeah.
You highlight 3 blocks. So are there 3 suspension points, or 2 plus the number of products times the last one?
I see your point. I'm not sure suspension points are defined that formally. So I think it's just lines in your code where where you're calling a suspending function, and so where the calling coroutine can suspend and later on resume. So let me go to a little bit of a sidebar. So this is a little bit of invisible magic, right? The suspension functions and also the this arguments. And so as you'd expect from JetBrains, they have special support in the IDE. So on the left in the gutter, I think it's called, you see these icons where the IDE tells you where the suspension points are. And on the right, you see that coroutine scope, the block after it has a this, is handed a this object. So basically the block after coroutine scope is called on an object, which is takes a little bit of getting used to, but it's really powerful.
But can you also really access that this from within that block? Can you say this dot and then you
Yeah, absolutely. Yeah. And sometimes that this is created there, but in this case it's the outer. It's it's a new. It is created here. Yeah. As a child of the outer this. Yeah. It's a really powerful pattern, not only for this kind of programming, but also because extension functions allow you to add, behavior, whatever you want to do, to something from a different module or completely different library. So,
Yes.
yeah.
Could you have put the await or the second map also in the first function? Because we now map twice, whereas I think the result from the async call in the first map would also return the same deferred as is being operated on in the second.
Whether it's two maps or not, it's no. So the second map happens after will be called after the coroutine has started.
For all of the product names
Yeah.
in the list.
Yeah, I think they can be combined. Yeah.
It's like two for loops. The first one you launch all the requests, and the second one by one you await all of them to complete.
Yeah, what you don't want to do is await the first one immediately, because then it will be sequential processing.
Right, so that answers my question.
Yeah, okay, yeah. Okay, so something else. Have you ever, had a program fail with, somewhere deep in a library, and then you look at the stack trace and it just says, well, this asynchronous task, couldn't be, some arcane phraseology, and it doesn't tell you anything about where it failed. For instance, we had that today in our logging library that couldn't get to logs.io and then barfed some incomprehensible stuff. I think so. At least the IDE shows you a special async stack trace, right? And even shows some of the. I'm not sure whether it's readable in the lower right, but. Shows you the underlying continuation magic going on. So that's a little bit of the stuff that the Kotlin compiler creates and what really runs on the JVM. I'll zoom into that later on a little bit. But the stack traces that I've seen so far at least show the stack trace as far as the suspendable functions go. I don't think they go beyond, to outer coroutines, but that would be pretty hard, I guess. But so this is already much better than a very generic scheduling exception. Yeah, little bit, zooming out. I showed some cool, nifty tools and stuff. But why is this important? Well.
This is part of the presentation.
Yeah. I didn't have a clicker. I thought that would be, yeah. So, I don't need to tell you why it's important for UI programming, right? That goes without saying. But on the server side, it needs a little bit more argumentation, I believe. Jvm Threads Are Heavyweight, which is, when you're having a technical design discussion and you think, your solution is cool and theirs sucks, you just say, yeah, but it's too heavyweight, right? So it can be very intangible. So let's see what that means, and then of course with respect to memory and CPU as well. So a JVM thread, you can just ask the JVM, how big it is. So it's by default 1 megabyte, give or take. And for some frameworks, you need to set it to 2 megabyte, for instance. So how many threads can you create? You can. I guess when you have a BV server, you can have 1,000 threads. But then if you need 1,000 threads for that peak load, what is that memory doing if you don't have that load? So you get quite low utilization of your resources. Utilization, you spend much more than you need. And at some point it just ends, right? So a little bit of history. This is Apache HTTPD. Does that mean anything to you? It's old school. It used to be the web server. This is a really old graphic. It even mentions sun and stuff like that. So this is up to 2005, and Apache is the blue line that just seems to keep on growing. And the short story is that pre 2.1 or something, their model was 1 thread, 1 OS thread per request. And in a JVM application server, you're processing requests. But a web server has to serve, all the CSS files, the images, everything. So, and with modern applications, they do a lot of requests concurrently. So 100 requests at a time is nothing. Of course, this is a long time ago. But the point is that beyond, I think, 250, the whole server was just only doing context switching, saying now this thread can run. Oh yeah, you've had your share, now you can run. And that context switching took up all the CPU time. So basically, it just didn't work beyond 250 threads. And then Nginx came along. That's familiar, right? Nginx. And guess how that was implemented? With basically 1 thread running an event loop. Yeah, and that could handle so much more. So that's a rather dramatic example where 1 thread, a thread-based processing really didn't cut it. Of course, Apache, the web server, came up with several different processing models, but that's a different story. So, CPU, amount of requests at a time, resource utilization, but, use cases. So when you have a lot of devices, notice I'm not using the word IoT, but or maybe mobile. So that's important. If your clients are on a slow connection, because slow connections means that your requests take potentially a really long time, and all that time it would be, keeping a precious, heavy thread unoccupied. If you don't agree, please tell me, right? Because I ask myself this, why are we doing this? If your application consists of lots of little servers, notice I'm not using the word microservices, but so if you have a lot of, your application consists of a lot of HTTP little servers, and you want to run them on shared hardware, virtualization, this is 2019, then it's a huge waste if they all need this big thread pool. because on the lower OS, it's still an operating system thread. You know, that there's limits to what virtualization can do. So you'll get low utilization if you don't do that. Yeah, and when you want to do more with less resources, right? Just how much you pay for your cloud services. Apparently, I haven't seen this personally, but with asynchronous programming under load, your curve of response times, it's much more predictable. You don't get outliers that are suddenly, basically not being serviced. And yeah, when you're working in distributed systems, you know, a local call is completely different from a call to a different server, you know, which takes time, which maybe you need to, you know, break off if it takes too long, because, you know, that will happen, or maybe you need to cancel it because it's outdated. So that's also... Do I miss a reason for asynchronous concurrent programming? Fun! Exactly, yeah. Why didn't I think of that? Okay, coroutine leaks. We have a coroutine that calls a function, and as a result, a few coroutines are started. And let's call it the main coroutine ends at some point, and one of the threads has thrown an exception or errored or whatever you call it, and one of them just doesn't stop. It's the why doesn't my JVM hold problem. I've been there, so it's quite easy to especially if you have a program that runs for a really long time, right? If you write the software for a nuclear missile, you don't need to worry about this stuff because, for servers, they run for a long time, and if you even lose some threads now and then, you know, it will eat up your resources.
That even when all your threads do finish, if one of your threads
exactly, yeah, good question.
Rollback all the other threads.
Yeah, exactly, yeah.
To a database transaction.
Yeah, but you can't, yeah, so please hold that thought. I'll come to that soon. But so this is the bad case, so if you don't do something special. So there's a really interesting article on this, and they compare this to programming with Go2. But that's a really old reference. But it's bad. Oh, hey. I guess something went wrong with my diagrams. Nee. So I'm bringing into, what's the word? Recall this example. We have the root coroutine at the top, and within that a child coroutine. Coroutine scope, sorry. Right? And so that's the mechanism which helps us here. We have a root coroutine scope where our main coroutine runs in, and within that a child coroutine scope. And so at the end of the child coroutine scope, we know for certain that all the coroutines that have been started within there have ended. And if not, we have means to make them end. And to come to your question, what if so? The idea here is that we have 4 coroutines that have been started, and the third one throws an exception, and we want that the other 3 are ended as well. So that's the default behavior when you create a coroutine scope, but you can also use something that's called supervision, which is familiar to people who do actor programming. And then you can just appoint a special exception handling to this this one individual coroutine. Does that answer your question? Oh, sorry. Yeah.
Yeah.
And what I found surprising is that because these suspendable functions, they just throw exceptions. So there's no error value that you need to smash into another error outcome. It's just exceptions. Yeah, so that's structured. Yeah.
Can you also just use try catch from call?
Yeah, absolutely. Yeah, yeah. The first time I saw that, I thought, what? Yeah, yeah. I'm not sure I have an example, but we can look at something. So, you know, the bad thing was like goto, right? Goto considered harmful, stuff like that. And structured programming was the solution. And so this is called structured concurrency. And it's what Go routines do not have, I don't think yet. But the general consensus is that adding this makes it much more manageable. Okay, concurrent programming. So a little bit, yeah, zooming out. I've spoken about suspendable functions, coroutines. So what else is there? Yeah, so there are flat mappable things. Yeah, I'm not sure what the best word is. You can call it monads. You can call it completable futures. You can call it, I think in JavaScript it's the and then, or the then.
Then.
Then, yeah, exactly.
For both map and flat map.
Yeah, exactly. Yeah. So that kind of handling, right? Asynchronous programming in that way. So we have promise, as I said, completable future, but streams and data flows are also in that category. Then we have actors, you know, Erlang, Akka. By the way, in Kotlin coroutines, there's also a little part of the library that offers actors, which is especially useful for managing state that you need to access concurrently. If you're interested in, yeah, well, no, never mind. So we have coroutines. So in Go, they're called Go routines. Some people call them fibers, which, you know, a thread, a fiber is a small fiber. So, green threads. So that's, yeah, there's some history there, but I won't bore you. They used to be the way the JVM was implemented, pre 1.2, I think. So communicating sequential processes, it's a mouthful, but when you use CSP, it's very easily to confuse with CPS, which, yeah. I'll dive into these later on a bit more. How are we going for time? It's fine. Or do we need a break?
I think we're still good, right?
Yep. Cool. So those are channels within Kotlin. I'll show you how they work and what the idea is. And then you also have effect systems. Some of them are monads, are flat mappable, so it's a little bit... I think Scala Zio is an effect system, right? But then a monadic one, so yeah.
Can I ask one thing?
Yeah.
So you also have like Vertex or Node.js. Where can you place them?
So Node.js, I think...
The event loop.
Yeah, exactly. So I think as far as concurrency concerned, Node.js is pretty similar to the browser, right? So in the browser you have one main thread or whatever you call it. And there is still some other threads processing when you do I/O and when you are running web workers. So the interesting, so a little bit of segue, Kotlin is multi-platform. So you can run Kotlin coroutines on the JVM. You can run them in the browser. I have some demo code I can show you. It's super interesting. And you can run them natively as well. And so that, personally, I find that pretty impressive because the JVM potentially has a lot of threads. The Node.js and the browser, yeah, primarily only one. And still it can run on all of those. Yeah, so one interesting thing about coroutines, using them you can implement all the other constructs, which makes them really powerful as something that you put either in, you know, really low in your technical stack. So these are the options in the compiler. So it can do some trickery while generating the classes. You can use meta programming, a bit like macros, and you can put it in the runtime. And so this is coming to the JVM. It's called Project Loom. So, you know, a loom is een weefgetouw, so, you know, threads, fibers. But so it's a huge undertaking, and it will take, you know, it will take years before it lands. But if it does, potentially all our old blocking code suddenly is magically asynchronous. So that's really hard to do, but it's momentous. And that's based on coroutines. Yeah, so ta-da! This is Java. So this is code that will, yeah, but it's service level code. So this is we see that they chose to implement structured concurrency, right? There's the continuation scope, and yield is the point where coroutine suspends. If you're not calling a different suspendable function. So yeah, that's really interesting. What that will mean for all kinds of other concurrent programming. Okay, so how do they work? Because it's magic, right? So this is a very simple suspendable function. So we do a print line, then we call a suspendable function, doesn't matter which one it is, and we do a print line afterwards. And so what I would expect is thinking, you know, it can suspend and allow, you know, other processing to go on in the middle. So the lines before that, up including the call to the suspendable functions, I expect that a little bit of a, yeah, I don't know, subfunction or to run as one, and the lines afterward. So these ones I expect to be run as one, and then some kind of a break potentially, and then these ones. So I'm sorry to what's the word? Confront you all with this. So this is the JavaScript that Kotlin generates. I told you, right? It's multi-platform. So when you run it in the browser, this is the implementation. And yeah, let's try, you know, let's look through the oogharen, squint a bit, and then you can tell that it starts with this switch with based on a state variable. So it's a state machine. And we notice here it starts with case 0. These are the lines, you know, the before the suspension point, including. Before it calls delay, the suspendable function, it sets the new state as 2, and then it will, it's a do while. It will enter the switch again and process from here. So I think this is the continuation, which is the lower implementation block that makes continuations work. And that will be implemented by the JVM.
I have a question. I'm not sure if it's relevant, but I do think it does make me wonder. Because if I sort of return in case 1, so I finished step 1, and now I suspend, and you do some other things, and when you have a relevant result for me, we continue, right? So you go to case 2. Is that what happens?
I haven't run this code concurrently because I do wonder about the if result equals coroutine suspended. Then we return that, and then we will be called again. And I'm not sure how that works.
Yeah, because how does it know which state it accumulated during the first one? Because if you return, then everything is gone. So where does it get that?
It's easy to analyze. I've got the code for you.
All right.
Yeah, but so I didn't get around to that. Yeah. The idea is that you have an intuitive understanding that what the machinery is underneath. Okay. So coroutines, that's nice and easy, but I've told you about channels, right? Which are interesting and are not in themselves part of, for instance, Scala programming. There's something called flows in Kotlin, and both are rather newish, especially the flows are being developed as we speak. Oh yeah, and the hot and cold metaphor, it's traditional in RX and streams programming, and it's hard to find a different, clearer, but hopefully you'll have an understanding after some explanation. So let's start out with a sequence. A sequence is, so here we generate, the famous or infamous Fibonacci, which is, the 1, 1, 2, 5, etc. Series, right? So we start out with an initial value, 0 and 1, and then we add the previous, and that will be the next value. So a sequence, it's a little bit like an iterator. It's a lazy collection. That's a different way of thinking about it. It's potentially infinite. And when you think about it, it's fold, is that familiar? You have a lot of values and you condense them into one. So this is the opposite, basically, an unfold. You start with one value and out of that you create a lot of them. We call our sequence. We map some, unnecessary transformation. Take 3 values because we don't want to wait forever, and then process them. So these are called intermediate operations. So at this point, no work is being done yet. And these are terminal operations. So this is where the processing really starts. I think in RX, this is a little bit like where the observable is subscribed, right? Or yeah. And so note that when we can call it again, which is not the case for all kinds of constructs like this. For instance, you can't with channels. And in that sense, and if you do, all the work is being done again. So you're not sharing that work. And that's important if you're, let's say, in a browser application and you call the server and you want to show, transform it a little bit and show it in this user interface component and here. and then you say you're using RxJS like I've done, and then you say, why is the server being called 3 times? And so that's about this kind of stuff. Is it shared or not? Is it run every time or not? Yeah. And yeah, in this terminology, a sequence is called. So until we call this terminal operation, nothing is happening yet. So the sequence is called because it isn't doing anything without you. So that sounds a bit like Sleepless in Seattle. I didn't mean it that sad. So these operations are intermediate, and these are terminal. Yeah, so for each is clear that should be terminal, right? Because you're not returning any values anymore, so you better be doing some kind of side effect. And for all, and count for both, it's the case that you need to know about all the values. So that also implies some kind of for each, you really need to have all the values available intuitively. Yeah.
As long as the sequence is not infinite.
Sorry?
If it's infinite,
Yeah, then you have a problem. Yeah. That's why I did take 3, right?
Yes.
Yeah. No, that's true. Yeah, so some people would say that it becomes hot in the terminal operation, as in, there's something going on inside it. So this is an alternative implementation that I find interesting. So we use this sequence builder called sequence. And we start out, our block is called on a sequence scope, which is a variation on the coroutine scope. So yield is where we return a value as part of the sequence. So it's a bit as if our get next is returning here, a little bit. If you see a sequence as an iterator. And oh yeah, really important, that's the suspension point here. So you notice that even though sequence is not asynchronous, it's blocking, still it's very integrated with suspendable functions and coroutines.
But it's not in your function type right now.
Yeah, so I'm going to point a little bit. I think from the top of my head, but I could be wrong. That this block, if we click through on the definition of this sequence builder, then this anonymous function with receiver type will be annotated with suspend.
Okay.
Because otherwise we'd have a problem calling a suspendable function here.
But the sequence magically erases that.
Yeah, exactly. Yeah, exactly. Yeah. But so I'm rather impressed how this suspendable functions coroutine thing permeates the whole toolkit of JetBrains, even the standard collections where you think you're not using coroutines. Yeah, and so this took a little bit of getting used to for me. Sometimes, yeah, you do a while true, and yeah, that feels what while true, but it never ends. Yeah, well, it's a lazy computation, so yes, it ends, namely at the suspension point. So that, and of course, a var. So yeah, this is an imperative version of the other one that was functional. But the interesting thing is the previous solution is functional, but when you click through to the implementation, guess what? At some point it becomes imperative again. So it,
I have a question.
yeah,
Because at some point you do take 3 and you get 3 and you continue on your merry life.
yeah. What do yeah?
Yeah. But this guy's running in the background still. While true, while true, while true.
Is it? Yeah. So I think there are two answers. Yes, it is, but there are plenty of coroutines. And no, it isn't, because there is a suspension point. And so that's the point where it can be told, okay, so this is it.
But so
And that's
you
part
can
of the-
also terminate.
Yeah, and that's part of the semantics of sequence. But we'll see it with flow again. Yeah.
So it will clean up the memory associated with this coroutine.
Yeah, and good question. So, memory leaks, etc. It's also in this sequence scope. I think that, I'm not sure actually.
Isn't it just cleared when the sequence is cleared by the current object?
Yeah, you're right. Yeah.
Ah.
Yeah, so, good question. So, you're right. There's no concurrent processing going on without your calling functions there. It's blocking, and it's all part of the calling thread or coroutine. Yeah. Okay, flows. So sequences, they feel a little bit like streams, right? But they're blocking. They're blocking. So flows are like sequences, but non-blocking. So here we use a flow builder, and we have our suspending function again. So this block again is a suspendable block from where we are calling it. Emit is where we create a value, which is a bit like our yield previously. Emit again is a suspendable function. Interesting to note, does the term back pressure mean, yeah?
Yes, and this is the equivalent of creating a new server, and the emit would be like the subscribe next in the direct RxJS world.
Come again?
If this would be the equivalent of creating a Loom server and in RxJS world, and the emit would be like the subscriber.next call.
Yeah, it's very similar. Yeah. Little bit of a segue. So you were comparing it to Rx, which is a bit like the, what's the word? The godfather, the gold standard of stream processing. So a lot of APIs just say, okay, that's cool, we'll do something similar. And I'm rather impressed how Roman Elizarov and the people at JetBrains are, taking what's working, but also reconsidering some stuff. So I'm really eager to see how they'll design flows further. I think I have a slide later on, but one of the things they would like to improve is with observables. You have this, am I working on a hot observable or a cold one? Which, at least for me, is really error prone. And they are trying to come up with an API that really makes it really clear which of the cases you're dealing with. And another one is by default flows are not concurrent. So when you call map and stuff like that, it's the processing, the default processing is all sequential. And they are adding parallel processing, of course, or parallel or concurrent. But they, again, they want to make the standard case really easy to use. And I think that's super cool. Back pressure. So in the world of streams, that's really important. Little bit of a big picture. if I have different components processing data from devices and databases and stuff, and I'm a downstream processing node, and I just can't keep up, it's nice if they start delivering my work slower. That is if you have a buffer in between, but yeah, let's not get into that. But it prevents, so if you don't have that, for instance, I as a downstream processor could run out of memory because I'm just overloaded with requests. So that's the idea of back pressure. And implementing it with, for instance, actors like Lightman did is super complicated because while your messages are coming downstream, you have to communicate upstream how much you are ready for. You know, yeah, okay, I'm ready for a few more, and then that has to go upstream. The interesting thing is here with coroutines and suspendable functions, if you're not ready for it, the upstream will just suspend. And so that's interesting. So recall our sequence. We have previously, which we could run multiple times. So let me stay here. We have this flow of ints, right? And again, we have intermediate operations that don't do anything yet. It's only when we call a terminal operation that really the work is started. We can. I thought I'm going to point. So here the work is done, and if we do some printing here in our flow, in the definition of our flow, we see that it started here and not here. And we'll see that here it started again. So the outcome is not shared by default. So a flow is called in that sense. Unless you do something special. I'm not sure this code is super interesting, but this one. Yeah, so let me magnify this. Oh. Yeah, again. I'll come to that later. Okay. So we see that there are quite a few suspension points, as I already pointed out. Yeah, and I added, when this flow is started, we'll print a line. And I'll use my poor man's RX marbles again. So we'll get a sense of how many coroutines are working here. And so we see, is this readable? I can, here after one, this starting is printed. Then we get a lot of values. Then we get 2. And then starting is printed again. And they're all in the same color, in the same column. So they're all on one coroutine. So by default, it's sequential, it's simple. And when we come to channels, which are quite tricky to program in, that will make sense why, having it sequential by default, non-concurrent, helps in making your application code obviously correct, instead of puzzling why isn't this doing what I think it should be doing. Does that make sense?
Yeah, so is this a bit comparable to, say, task in Scala, where there are like a future that's not either?
Yeah, flow, it's more like an observable in that sense,
Oh,
right?
okay.
Yeah.
Oh, because it can emit multiple results, yes.
Yeah, it's restartable, but there's no explicit run method, or it's something like that, which I think task has, right?
Yeah, so is there an equivalent for that in the coroutines, where you basically have a non-eager block of code that you want to run concurrently?
Yeah, so a little bit of a segue with recall our coroutine builder launch. There's an option where you can say lazy, and then it will only be started once the result is accessed,
Okay.
or when somebody awaits it. So, like a lot of in this toolkit, it's somewhat similar to the stuff in the Scala toolkit, but okay.
I think 1 hour 20 minutes, Joost.
Yeah.
We're at 1 hour.
Okay. Shall we have a drink? Yeah.
A small break.
Yeah. Cool. Yeah. So where were we? We've been looking at sequences, right, which are a little bit stream-like, but they're really just lazy collections. We've looked at flows, which are much more like streams. And so what they have in common is that both are called, only when we call them with a terminal operation, at least in the default, they start doing stuff. Flows are, what this evening is all about, asynchronous non-blocking, and sequences are not. But I did start with sequences because it's a nice transition from the familiar world of collections, lazy collections, stream, and then a non-blocking stream like flow. And yeah, I already mentioned that the goal of flows is that they're much more easy to use and easier to analyze than our next. Sorry, one more slide. What I wanted to say, much more easy than channels, which I'll be going into. So a comparison with observables, the gold standard of streams. So as I mentioned, the API, they're trying to come up with an API that will make it really clear, am I dealing with a hot one or a cold one? I think we already saw how it's integrated with coroutines. You have a lot of suspending functions, and that helps them implementing it as well, providing the back pressure that I mentioned. The theme of ease of programming is that they, by default, the happy flow operators are all not concurrent. So by default, the processing is sequential, as we saw. The concurrent processing is coming, but they want to have it very clearly separate, because it makes it potentially more complicated. Yeah, so channels, which are not that easy to use, and I hope we'll see this. We have a simple channel of integers. We create one here. Within, we fire and forget a coroutine. And while we continue on our merry way, that coroutine will start spewing values. And we are in a calling coroutine, And so how do we get access to those values? Because two threads can't just share data, because then you get data races and or that you're clobbering each other's values and all kinds of hard to debug stuff. And so channels are a bit like special concurrent collections where so if you remember one thing about channels, they're for communication between threads. So here, this is a bit like the emit. So this is where we send a value to the coroutine. Again, it's a suspension point. And we have a special value here, which is, the end of this channel. Here there's some invisible magic going on, because a for loop in Kotlin expects an iterator value on, I think it's the same in Java, on the collection. And this channel has a special kind of asynchronous iterator that will produce values from the channel if and when they are sent. And if there's no value, this code here will just suspend. So that's what's going on underneath here. So it's you can also call, I think, receive or something on the channel. So again, because of the suspending functions, it's back pressured. This channel here, we don't provide it any special arguments. So the default of a channel is that it has a capacity of 1, and that's called a rendezvous channel, because it's where the threads meet each other. So one, I'm going to point. So this one here has, let's say it has just started, it has a value 1, and so it's sending here that value. Let's say this one hasn't started yet, so it will just suspend here. So this whole thing will be frozen in time, basically, until this one has read 1, and then this will continue, and the reverse is also true. So if this hasn't sent anything yet, then this one can receive, but it will just freeze here, suspend. Maybe that already gives you an inkling of the challenges of correct programming here. If not, we'll see them later on. But we do have back pressure. The upstream processor. If this one is slower, this one will be just as slow, just to offer results piecemeal.
I have a question.
Yeah.
So, when you send V, it is calculating ahead of time, right? So
Yeah, so that's really not especially necessary. I had a version where I printed stuff.
Okay.
Yeah, so that's immaterial. Okay, so again, the wrong one. So, it's I didn't put it in. That's a bit too challenging. Oh, and it switched. Well, at least it's deterministic, or I am deterministic, which is an unsettling idea. I think I have free will. So let's run it. Yeah, so the colors and columns are different coroutines. And we see that, first something is sent and then something is received. I have no idea why it's doing 2 and then, 2 and 2 and 2 and 2. So, yeah, I would have expected it to do it interleaved.
Could that be the race condition between the two things?
Yeah, I'm not sure what you mean by race condition, but I think this should be...
Maybe it's a channel buffer?
Yeah, so my understanding, but so that's something to investigate.
I think it's,
My-
it's printing the line and then the channel stops sending by the back pressure of the loop.
Ah, that's a good one.
That's why.
Yeah,
First it sends one,
Yeah.
it gets in the
Yeah.
cache,
yeah,
and then it
Yeah.
tries to send one.
yeah, exactly. Yeah, good point. Yeah,
Maybe when you switch them.
yeah.
If you switch the print line and the channel send, will be.
Yeah. Cool. So let me see. Do we want to change something here? Would it change something if I put a delay here in between? What do you think? I don't know.
I don't think so.
Nee, right? Yeah, because it will just wait until it's ready to receive. Yeah.
So the initial send wouldn't suspend because at that point in time the buffer is still empty. So the one that's just pushed, it is that's one can be pushed just fine. So it doesn't suspend. Then the next time around it does actually suspend. So that's why I think.
Mm-hmm. Yeah, I think it's meant to have a capacity of 1.
Yeah. So
Yeah.
the initial push is actually successful.
Yeah,
And then that's why it continues.
yeah. I'm not sure I have slides about it, but there are all kinds of variations on this. So for instance, do I have a slide on it? For instance, there's, so yeah, I do, yeah. Let me wait for some of my slides. Okay. Okay. Something fishy going on. Okay. I think I already mentioned this. This is where they meet each other and suspend otherwise. So, it's some kind of synchronization, right? I do something, you do something. But there are also buffered ones where you can say, my buffer is, let's say, 10. And then if the sender has sent 10, but none of them have been received yet, again, it suspends. So still you have back pressure. But for instance, there's also something that they call a conflated channel. And basically that means that by default it keeps the most recent value. So channels are inherently hot, whether you're there or, calling it or not. Something is processing, is sending on the other end, which makes them also hard to manage in your code, by the way. And conflated means that if I start receiving from the channel, sometimes you're just interested in the last value. So let's say I have some kind of home device where I'm keeping track of the temperature. I don't care about the whole history of the temperature. I need to know the history, the temperature now, the last event, and update and display or whatever. And so if I have two user interface components, one shows the temperature as a number and the other as a color, you know, they both want to have the most recent value. So that's a slightly different, yeah. I don't think I have, I have somewhere else. So channels by default are like queues, right? In system programming, we all know a queue. If I take a value out, you can't take it out anymore. It has been consumed. So in that sense, they're useful for work distribution. I'll show an example of that. But sometimes you want, you know, if you're doing front-end programming, you want that the two UI components have different views on the same data. So then that's something they call a broadcast conflated channel. So that's like, you know, in system programming, like a topic. And it's also very stateful, right? It's not so much a computation. There's some state there that's being transmitted. So this is an example from Roman Elizarov. So he's the tech lead of Coroutines at Kotlin, and he has given some talks on the subject and written great blog posts. So I recommend that you, if you're interested, you read them. So this is from his talk. This is an example of using channels to distribute work. So we have a fixed number of workers here. So they're chugging along. They're coroutines, obviously, and we have one coroutine here that's distributing the work to these, you know, they're I don't know, screen scraping or whatever you call it, downloading stuff. And here the result, and you know, this one gathers from all the workers and I don't know, stores it in a database or something. So we have here for the whole thing, one channel goes in, this one reads from this channel, sends here and reads here. Yeah, makes sense, right? So it goes from here, there, like this. So this is where we start so before this line that I highlight here, this function is an extension function on coroutine scope, and that already gives us an inkling that probably in the implementation coroutines are started. Because that's what the coroutine scope is for, right? To contain them. So we create two channels. And then here, let's say n is 5. 5 times we launch, you know, fire and forget these worker coroutines. And we provide them with these channels. So we can communicate them with them. And especially the downloader can communicate with them. And the downloader we provide with, you know, that's the channel on the, on the left, where what needs to be done is sent. So this worker, again, it's an extension function on coroutine scope, and the implementation is we launch a coroutine, and with a for loop we start receiving from the locations, which are the stuff we need to download. Then we have this function where we do whatever, you know, some heavy stuff. And here we have a send channel where we send it back. So that's all quite clear, right? This one is a little bit more interesting. It's the one in the middle. So it has 3 channels. This is where it gets the work that needs to be done. And these are the ones to communicate with the workers. And so it's a little bit more interesting because it needs to process from 2 channels. So you can't do a for loop, right? Because so this is the way to do that. It's I think it's called select expressions. It's something that's available in Go as well. So there's a receive block here and a receive block here. And so here this is pretty obvious, right? The references is, the outer, the main work to be done, and it just translate it and send it through to the worker. And here we receive the downloaded content and do some storage. So let's run it. Let's see if it again. Okay.
Until you end the presentation.
Yeah, exactly. Yeah. Yeah. Let's see. Yeah. Wonderful. Okay. So again, we see the suspendable suspension points. So I'll run it. So this is an example from Roman Elizarov. And after 4 results, the processing stops. Yeah. So not to put him down, but he's the lead of Kotlin Coroutines. This is the code from his presentation on Kotlin Conf, and it contains a deadlock. So not locks as in, locks on an object, but it's a communication deadlock. So what happens is that all coroutines are waiting to receive stuff from the other ones. And I'm really impressed how he dealt with this. So he really, first he started questioning, do coroutines and channels work correctly? Then he re-implemented it in Go, same result. He implemented it in akka actors. There it worked because those have an unbounded inbox. At some point he started using formal verification. So one of the ways to fix it is to make one channel unbounded. So the default, remember, is that they are rendezvous. So they're which, intuitively can easily lead to everybody waiting for everybody else. And so buffers already makes it less often, but still deadlocks. And unbounded channel fixes it. But then we lose back pressure, which can lead to out of memory problems, because it will just send and send and send. That's a challenge. And there's also a different solution. There's this place where we are listening to 2 channels. And apparently if you do it the other way around, that makes a big difference. Yeah, exactly. So
is this a sales pitch or?
No. So so that's also what JetBrains says. It's really powerful for communication between concurrent processing. There are some alternatives, but most of them are like this. So this is called message passing, and guess what is also message passing? Actors. But I think it means that channels will mostly be used by libraries which provide an obviously correct way of programming on top of them. like flows or other constructs. Yeah.
This whole channel environment could be compared to some sort of context, CPU context switching coordinator.
Yeah, so let me see if I understand correctly. It can be compared to a CPU work coordinator.
Switch.
Yeah, context switch. So it's a pattern of distributing work and gathering the results, right? Yeah, so it's really common. Yeah, it's a pattern. But so I do think channels are, you really need to know more to write them correctly. So I think a lot of applications won't be using them directly, but indirectly under the hood. So a little bit of a segue. If you think about coroutines and channels on the one hand, and on the other hand you have actors. How do they compare? Yeah, so I'll show, I have some slides later on, but basically it boils down to an actor has a built-in channel, which is the mailbox, and that's unbounded, and hence you don't have this kind of communication deadlock. And a thread, a lightweight thread, and an inbox in an act are encapsulated in an actor, and that whole thing is named. You can refer to it, and so I found a really interesting paper comparing them from Philip Wadler, and so channels are also some free floating inboxes basically. And those are named, and so multiple threads of communication can consume from one inbox. So, like often with this kind of programming, when you compare it to a different approach, you encounter similar constructs, but yeah, a little bit different. Yeah, so I showed that this way the communication deadlock doesn't occur. Oh. Okay, so what can I do with coroutines and channels and flows and that toolkit? So then frameworks and APIs are important, right? For a few years, Pivotal and Spring have joined, the reactive bandwagon, or started implementing stuff reactively, and they came up with what's basically their variant of RX Java. Spring Reactor, so Pivotal has been endorsing Kotlin and coroutines officially quite recently. So the last release of Spring Framework contains coroutine support, and the upcoming version of Spring Boot will contain coroutine support, and I'll show you some examples. And under the hood, everything is based on Spring Reactor, their observable implementation. But with the extension functions of Kotlin, you hardly notice. It's really smooth, and the way you see it are suspendable functions and flows. So if this interests you, follow Sebastian Deleuze. He's very much the person who's pushing for functional programming, Kotlin, coroutines, etc. within Pivotal. And he's coming to a Kotlin meetup in Utrecht on June 3rd. So that's interesting, I think. So this is, so notice the annotation flow preview. So JetBrains makes me, it's a bit like an end user agreement. Yes, I acknowledge that this can change. So flows are very early days. This is the new functional way of creating controllers in Spring Boot. And instead of the standard router DSL, notice it starts with CO, and then suddenly these functions can return either flows or be suspendable, or both. So drilling down a little bit, this is the function, the top, this one, right? And I think I need to scroll a bit. So of course it starts out with the path, and then we have an anonymous block that is a suspendable function, as we can see here. And it's a function from server request to server response. Well, exactly what you expect. So that's super simple and powerful, I think. So, drilling down, this is one of the functions that's called. Notice that it's suspendable. And yeah, they don't annotate it, but it's a flow of, what is it again, person or whatever, user or so, something like that. But there are also functions that return one user, I think it is here. And then it's just suspend with a return value of user. So no future or mono or stuff like that. This is, so that's what this returns, and this one, takes, in this case, a flow and just awaits the result. And yeah, I hope it starts streaming it out to the client before everything, but I haven't checked.
You have to extend another repository interface then, because the find all is now an iterable.
What do you mean it's an iterable?
Find all now from Spring Data repository now returns iterable.
I don't think this has anything to do with the Spring Data repository, but I'm not sure. I haven't drilled down, so there is integration specifically with Spring Data. I have seen, so I'll drill down a little bit more where you see where it, so it hooks into the Flux support basically. So here is our find all. Again, yes, JetBrains, I know this will change. Oh, I thought I had a highlight functionality here. So this is a Spring Data abstraction, which basically, as I'll show you, has maps the world of select database results to either Flux or mono, so mono is the future, completable future of Spring Reactor, and Flux is an observable, and this is an extension function that first calls, says give it to me as a Flux, and then I'll transform that into Kotlin flow. So yeah, quite obvious and boring, right? But I have to say, I'm rather happy about the prospect of this kind of programming. I don't have it on the slide, but Spring has Pivotal has started work on asynchronous, an asynchronous form of JDBC, which will make a huge difference for async programming. Okay, so that's Spring. Of course, there's Ktor, which is the web framework of JetBrains. There's integration with Java 8 completable future, with Spring Reactor, with RxJava and ArcJava 2, with reactive streams, which is a standard, right? So if I want to use the system integration stream processing library of from the Scala world called Alpaca, it implements this standard, and I can work with it in exactly the same way as I showed. Guava, I think, is used in the world of Android. I'm not sure. Swing. So why Swing integration? Well, apparently IntelliJ is built in Swing. So JavaFX, integration with JavaScript promises, with JavaScript animation frames. If that interests you, I have an interesting piece of code that I can show you afterwards. So that gives an inkling, you know, what can I do with this kind of stuff at the server side. Okay. So comparing them, sequence is blocking, but it's a nice example of something that's cold, just like the flows under, at the bottom. And channels are a way of doing of message passing, which is a programming model, concurrent programming model. So message passing is the abstraction that both channels and actors implement, and you can think of it as some kind of shared collection that can be shared between threads. I guess that's it. Coroutines are stable, really rock solid. Channels are, I don't think they'll change that much, and flows are really early days. So if you're interested in more, the coroutine guide is really good. Roman Elizarov, just follow him. He really spends a lot of time in making sure the knowledge of how this works is shared, and then just reading the issues in GitHub and the source really works well. This is more for over a beer. So that's it.
Thank you, Joost, for this extended talk about a lot of coroutines. It's nice to hear that you have tasted all the programming languages and can compare them nicely to coroutines. So, and I find it really interesting that you all had questions. So it was a nice interactive session, which is great. But maybe there are still questions left. So if you have any questions, you can take maybe a couple of them.
Sure.
Since Spring Web Flux, it works using some sort of observable approach, and if you make a bounded subscription, you have back pressure on it. Specify the amount of requests that will be made when you are creating a subscription for the flow.
Yeah. So as far as I know, Webflux does support back pressure.
Yes.
I
want to know, since Flux is Spring Web Flux object is wrapper is some sort of observable that does support back pressure, and also if you subscribe it against a parallel scheduler, you can have sort of parallel programming or What is the advantage about converting this structure that comes for free from the Spring Data?
Yeah,
Reactive
yeah,
Composer
interesting.
To flow, to
Yeah,
flow
good
in
good
Kotlin?
question. So it's early days, right? Because that is especially the flow. Well, no, let me start differently. I think that splits in two things. One, the mono, which is a completable future or something like that. And personally, I think that suspendable functions are quite a bit nicer, but that's opinion, I guess. Then when you look at multiple results, I'm rather impressed with the vision between the coroutine approach, to try to make it as obviously correct what you're writing as possible. And so they try to make the case of concurrent programming a special case that they, how to put it, lived in a special context. So to phrase it differently, it's a bit unkind to say, but Webflux is RX Java re-implemented. And I'm really intrigued by how JetBrains are trying to learn from what worked well and what can be improved and trying to rethink it a little bit. So that's what I would think I would gain from using this programming model.
Are there any other questions? Else we can do it.
Yeah, it's late, right? Yeah. Okay,
Yeah,
thanks so much. Yeah.